Hi, everyone. Welcome to Module 4 of Predictive Analytics. This week, we're going to dive into Supervised Learning 3, Support Vector Machines. So last week, we covered decision trees. We looked at the decision-making process and building and pruning decision trees. So actually going through that decision-making process, figuring out what are those nodes, those decision points that we get to, how do we prevent overfitting by pruning our decision trees, and then how can we take a tree and make a forest through the random forest model. So getting into ensemble modeling, getting into making basically one machine learning model work a little bit better by combining it with multiple other models. We also briefly talked about applications in business. So there's lots of applications. So just kind of getting out there what there is. Churn modeling. I can't remember all the examples off of the top of my head, but there were a lot out there. And I didn't get a chance to record the lectures after all the internet issues last week. I apologize for that. But hopefully the slides explained everything. This week, we're going to cover support vector machines, and I'm going to do things a little bit differently this week. So I actually found this really great video that goes very in depth with the support vector machine concept side. So I'm going to actually let that video handle it. It's a 20-minute video, and I've only got a few parts that I really want you to watch. I figured why recreate the wheel if there's something already out there. So I will link that in the required learning activities. Fantastic video from StatQuest. I believe it's StatQuest. If I was going to make an example, it'd be about the same example. So I'm going to have them take that over for me. In this video, I'm going to cover just really briefly classification methods. So go over what we've covered already, look at the evaluation metrics, and really getting into that model interpretation. And then some of the other learning activities that you're going to do this week, you're going to look at cross-validation techniques and the bias variance trade-off. So this video, you probably won't hear as much from me because I really want you to dive in and actually try a lot of these things. So we have covered so far a lot of different classification methods. Logistic regression, remember that one's kind of weirdly named, but it is a classification method. Decision trees, we built that tree into a forest to make a random forest. And then our final algorithm is support vector machine, SVM. And this one's really neat. Again, I don't love outsourcing my videos to other people because I like explaining things myself. I loved this video. So the one I'm going to have you watch is actually really, really well done. The basics of support vector machines are that we want to categorize data. We want to classify data, so classification method. And the support vector machine is that it's going to find the best way to find a physical separation in our data. And that's basically it. That's a 20-second overview. In this part of the video, I really want to get into what are we doing here? How do you know what model to use? Because that's really why you came to school. You can learn a lot of this online of how to actually implement the models, but the deeper questions of what model to use and when, that's really what makes a data analyst, a data scientist, an analytical thinker. So the way I always go about this is start from the very beginning. What problem are you trying to solve? Now, our first instinct as analytical people is that we often want to try to throw the fanciest thing we can think of at our problem. That's not always the best solution. So I've made a list of a few things that I would recommend you start with. And the first is, what is the goal of your analysis? Are you just trying to understand your data? Start with exploratory data analysis. You should start there no matter what. But just know if you're not trying to predict anything, you do not need a predictive model. If you are trying to predict, or if you're looking at future predictions, so you have past data and you want to make predictions on future data, yes, you would need a machine learning model. If you want to define relationships, maybe you want to know what features are most important, you want to understand the nuances within a relationship within data, that goes back to that exploratory data analysis. Maybe a regression model is good for your data. Maybe through decision trees or random forests, you can get to know the features that best predict your target variable. But by going back and understanding what problem you're trying to solve, this helps you understand kind of a starting direction. Some of these models are better than others at explaining what's going on behind the data. For example, decision trees are very explainable. Not just that it's easy to explain to a business user that doesn't know anything about coding or technology or anything, but it actually explains your data. It adds extra information. Support vector machines, on the other hand, while you can get a really great model off of it, it's a really great tool, it's not actually adding a lot of data to your head. I can't look at the output of a model and say, oh, now I get it. This is the best variable for this. It's starting to get into what we call those black box models, where we take our data, we put it into a black box, and we get some sort of output back. The next step is to look at what data is available and in what format. So I am giving you lots of different data sets to play around with. Some of them are ready to use right away, and some of them require some changing. You noticed in the wine data set, you needed to change the quality from a numeric value to, I believe we said if it was over 7, it's it's a 1. If it's less than 7, it's a 0. What about your other variables? Do you have categorical variables? Do you have numeric? Are they all scaled the same way? You noticed in the logistic regression, it worked better if you scaled them the same. Maybe you have to add in other data. So really understanding what data you have and in what format you might need it to do the model you're thinking of. And then how will this analysis be used? This again goes back to the initial question of what are you trying to do? But if you need to explain this to a business user, maybe a fancier model isn't what you need. Maybe it's a starting point, but you might end up wanting to use a decision tree or a random forest. Maybe a decision tree is a great one to start off with to just get an idea of what's going on in your data, but you would rather have a really efficient and highly accurate sensitive model, in which case maybe it's a fancier model like the SVM. This is where you have to understand, again, what are you trying to do with your data? And I keep saying this, explain it to a business user. And that's because a lot of times when you are a data analyst, data scientist on a team, if you are going to implement a model, you're going to have to explain it to someone and essentially prove to them why you are correct. And that's not as easy as saying my model's 95% accurate. You actually have to be able to explain what that accuracy rate means and what happens if something goes wrong. What if your prediction is incorrect? These questions are going to help you start to get there. This is just a little reference guide for as you start to compare these different methods. I put this type usually because, as I mentioned in some of the other videos, decision tree, we're using the classifier. That's what I've always done. I've never used a decision tree regression, but it is out there. It does exist. So this is just where you can kind of look and see, this is what I have, the data requirements, and just some notes. So decision trees are really great for explainability and feature importance, where random forest is more for that feature importance. You lose out on that explainability, but you still get some really great data on feature importance. SVMs require numeric data, and it's best for clearly defined categories. I didn't put this in here, but SVMs are usually pretty computationally efficient, I've noticed. They run pretty quickly. They do well with really small data sets. A few of you mentioned that the wine data set was big. That's actually a really tiny data set in comparison to a normal business use case. Logistic regression, you need ones and zeros. Linear regression, you need all numeric data. You can't deal with categorical, but decision trees, it does just fine with categorical variables in your features. Just knowing what data is out there and knowing that you can change your data if you need to. But remember back to, I believe it was week 1 or week 2, we talked about how to change data properly, how to start thinking about getting data into the shape that you need it. And then finally, I did get a lot of questions about these evaluation methods. So I am glad that you're looking at this because it is difficult when you're first starting out, especially. The first thing you should always look at when you're looking at a classification model is accuracy. That's the first thing. Always look at that. Just how many did I get correct over how many did I guess? But from here, this is where you can start to dive into the business problem. For sensitivity, the example that always comes to mind is the breast cancer example. So if I'm looking at the breast cancer data and I have a high sensitivity rate, that means I'm finding those true positives, those cases of positive results saying there is cancer. And that doesn't mean I'm not finding the negatives, but I'm optimizing for those true positives. Versus specificity, I'm looking for those true negatives. That might be better for an email spam filter. It's okay if an occasional spam email comes through to my inbox, but you better not send a real email to my spam. That's not a great thing to do. So it's okay if you get a few incorrect, but you better always get them. It's okay if you have some sorry, now I've got it all mixed up in my head. It's okay if you have some false negatives. There we go, false negatives, but you don't want to have any false positives. Versus the breast cancer, you want to catch as many true positives as you can. False negatives, sending someone home when they actually do have cancer, that would be a really bad thing. And then these other scores, a lot of them are actually built on top of each other. And when you look at that confusion matrix, if you Google confusion matrix, there's tons of great videos and stuff. There will be something that speaks to you. What always helps me is just picturing it as an Excel sheet, those rows and columns. Find what you predicted and what was true, and find the coordinate that matches. And then I always go back to what was the business case? What was I trying to do? And again, what would happen if I was wrong? 10 years in, I still ask myself these same questions. And 10 years in, I still don't have most of these memorized. It's okay to Google. It's okay to look things up. Just be confident enough at some point during this class to be able to explain these and know which one you might want to optimize for. And by the way, that sensitivity question, that came up in a data science interview maybe 6 years ago or so. So they ask these kinds of things. So if you're looking for that kind of job, just know that they will ask about evaluation metrics and which one you would use in what kind of situation. And then just so I can show you this image, but I'm going to leave a lot of resources in the learning activities as well. As we talk about overfitting and the variance trade-off, there we go. It's the end of the day on a Friday when I'm recording. This is what we mean. And it's way easier to plot things in an XY axis versus 3D and everything. So that's why it's always only two variables. But if you look at this graph, this XY line, you see how it's too perfect. This is an overfit line because if we suddenly get a data point right here or right here, it doesn't fit the line anymore. So my test data or my training data set is going to be perfect. It's going to be highly, highly accurate, but it's because my model is overfit. When I introduce new data, suddenly this line is never going to make sense. This middle one is underfit. It's got a lot of bias. It's only hitting these 2 points exactly, and everything else is off. Where this one, we're trying to balance it as much as possible. We want to hit the points, but we want to be able to generalize so that when future data comes in, we know where it's supposed to go. And that's the same thing for the classification methods we use. This one is showing the line, but you could use the same thing if you picture saying like this was churn and this is not churn. So like different sides of the line are different categories. This would be too specific. So someone right here might be churn, but they were scored as not churn, where this is actually representative of the data. So that was classification methods in just a few minutes. But yeah, go watch the SVM video. I hope you like it. I genuinely enjoyed it. And that is it. Have a fantastic week, and I will see you next time. Bye.